Hello and welcome. Today we're going to be talking about the natural numbers again, and we're going to be taking our axiomatic approach and building our algebra. And so the major goal here is we're going to be proving the associative. The associative rule, which is n plus m plus k is equal to n plus the quantity m plus k. That's an n there. Okay, so that's the proving the associative. The next thing we're going to do, of course, is also prove the commutative property. That is that n plus m is equal to m plus n. Okay, so these are very familiar, and again, so let's back up even more. So these are the two major goals that we're going to finish our video with. But before we start those proofs, what we really need to do is back up and again recall what natural numbers are and where they came from. So of course they are the counting numbers. So they're the counting numbers. And we had an axiomatic approach to them. And the axiomatic approach was that n1, the first axiom is that there is this number called 1. And I'm just going to abbreviate our axioms. n2 was this axiom that for all n that are in the naturals, in this set, there exists this sort of a next number, which is defined by this function s of n. Okay? All right, so there's a way to connect. There's a way of connecting one number to the next. Okay? So this is connecting. Between n's in our set. Okay? But there's rules to the way these things connect. Okay? First of all, n3, that 1 is not the next number of any for all n in the set. So we can't start. We can never have 1 be the next of anything. Okay, and so the idea is that this is basically saying that there can be no loops. We can't start with 1, 2, 3, 4, and have 4 be the next number be 1. Okay, so no loops. Okay, and that basically affects the topology of our number system. The counting numbers, of course, go on forever. They don't loop back on themselves. Okay, and of course that's a really key understanding here, is that when we're deriving something axiomatically, we're essentially saying what the thing can't be. Okay. Of all the possible systems of out there, the counting numbers have a really special structure, and it's defined by these axioms. The other thing is no branches, and that is if two numbers have the same next, then it implies that the two numbers themselves are the same, and this is essentially saying no branches. Okay, we can't have 1, 2, 3, and 4, 5, 6 both go and go to 7. Okay, 7 can't be the next number of any preceding, so we can't have and then 8, 9, 10 after that. All right, so here there's obviously a different sort of topology to this number line. Clearly, there are two kind of paths to get to 7. That's not allowed. And the next thing is that finally, the last axiom is that essentially, and I'll paraphrase here, the next in sequence will essentially get, or I should say encounter, all n, provided if you start starts at 1. Okay, so if you start at 1 and you go to the next in the sequence, and if you keep going to the next in sequence, you will encounter all the n. You won't skipping. So basically, this is a no skipping rule. Of course, you could imagine different sorts of number systems where you could skip from, let's say, 2 to 4, and then 4 to 6, and so on and so forth. So basically, your notion of next wouldn't be uniform. Okay, so that's our idea of the natural numbers. All right, and now what we're going to do is define the algebra. So our goal first is to define an algebra. The algebra. And just like we did up here, where we essentially define the natural numbers by excluding a bunch of things that we didn't want to happen, right? Like no branches, no loops, and no skipping. All right, this idea that 1 is the first number, and it can't be there can be nothing before it, and this notion that there are connections between. All right, we want to define an algebra that's somehow consistent with all of these things, and that makes sense. And from there, we're going to be proving the associative rule. And again, what we're going to be doing, as before, we're going to exclude. So the process will be to exclude all possible algebras that don't conform to basic principles of counting, basic arithmetic. And that, of course, is a central conceit of this entire course, which is that we're taking things that really essentially we learned when we were children, and we're picking them apart and saying, okay, here are all the possible things we could do with this set of natural numbers, but we're now going to exclude a bunch of those things and only consider basic axioms that lead to our basic arithmetic that we knew when we were children. So by understanding, by contrasting what we think is obvious with all the things that are possible, that we could possibly define, we can better understand what it is we're dealing with when we're talking about the counting numbers, basic arithmetic of adding, and the natural numbers. Okay, so let's get started. All right, so let's now write down the definition of the algebra. And again, the goal is that we want arithmetic, adding, to be consistent with notions, the notion of the next. And I'll put that in quotes. Okay, and what we mean by that is Sn. Okay. All right, so let's write down what that is. Okay, so the first condition we have, and I'll put this down, is literally that if I take n and I go plus 1, that is equal to the next. Before, we didn't have a notion that our algebra, i.e. our plus 1, was actually identified with this next number in the sequence. But now we're doing that. Okay. 2. We're going to also say that the next, this notion of next is going to permeate all other computations. So if I now take the next of any two numbers, if I take n plus m, I can take the next after I take my sum, or I can take n and add it to the next of m. Okay. And the idea here, of course, is that one way to characterize this is that the S function commutes with addition. Okay, and an aside, before we get started, I wanted to just go over briefly, algebra in general. So algebra in general is anything, and we have to define what is an algebra. Okay, we know that algebra is basically, we have to have two ingredients. And the two ingredients are as follows. And I'll just put them as capital A and capital B. We need a set. In this case, of course, the set is going to be our natural numbers, and B, an operation. In this case, it's going to be plus. And this operation is actually what we call a binary operator. And that basically a binary operator means take two objects in the set. So for instance, I can take x and y, all right, and then what we're going to do is and that's going to be set to some other, that'll get sent to some other value. And what we say here is that these two objects were summed together to create z. So the idea is we take some pair of objects in our set, and that pair somehow gets combined through this operation to create z. So in this case, we say x plus y is equal to z. All right, so it's this sort of plus operator here. Takes two objects and combines them together. And the notion here is that order in general matters. In general. So for instance, I could come up with a really arbitrary algebra. So let's come up with an arbitrary algebra on the natural numbers, and I'll just give an example here. So what I'm going to do is actually create essentially an addition table. So I'm going to start with n there and m there, right? And these are going to be my values. I'll start with 1, 2, 3, 4, okay? And there'll be another 1, 2, 3, 4 here. Okay, and so I want to know if I take n, and if n is in the first position, and m is going to be in the second position. If I take them together, I can say 1 and 1 create, well, I don't care, I'll say it creates 4. It doesn't matter, because again, this is completely arbitrary. I'm just making arbitrary assignments. If I take two objects in my set, it's associated with a third object. It doesn't have to make any sense. It can be an arbitrary pairing, essentially. So I can say that now 2 plus 1 is equal to 3, but 1 plus 2 is equal to 2. And so we see here, again, order matters. All right. So we see the way this arbitrary algebra is set up is that 1 and 2 and 2 and 1 do not equal the same thing. Okay. And the same thing here, I can say that now 2 and 2 equals 1, and I could just go through this whole thing and create completely just crazy stuff. All right, things that don't make any sense in any possible realistic system. But the idea is that arbitrary algebras contain lots of things. But the idea is we want to use these principles here, these two definitions that create my algebra, and see if we can throw out all the arbitrary ones and come up with one that really works well for our purposes. Okay, so I can just keep doing this. And here, finally, 4 and 4 makes 10,000. Okay, so there's a completely arbitrary algebra. Of course, we don't care at all. This will never be used for anything practical. But the idea is one could make such a thing. And now we want to find a way to, using these two principles here, produce an algebra that has that associative and commutative property that we know and love. Okay, so let's get started. So again, I'm going to write this up here again. These are our key definitions that create the algebra, which is that n plus 1 is equal to the next. Okay? And the other identity is that if I take the next of any two objects that have been summed in the naturals, that's equal to n plus the next of m. Okay, so those are my two things. And now what I want to do is take this. This defines my algebra, and I'll put that in a little box there. And now I want to prove the associative property. Okay, so the associative property is as follows: m plus k, the quantity m plus k, is equal to n plus m, that quantity, all plus k. So notice here we have n and m are already well defined within this thing. So really, k is the wild card. So what we need to do really is prove. So we're kind of restricting what our task to prove is. Prove that the above works. What I mean is this identity holds for all k in the naturals, right? And so we're going to do this. We're going to prove by induction. And so induction means we start at 1 at k equals 1, and then go to 2, 3, and essentially what we mean is we verify it for 1, and then and note if the identity holds here, this holds. If it holds for k, assess if it being this statement here, I'll put that with a star, if the star holds for the next in the sequence. Okay, so again, first we start at k equals 1. And this works, this process of going next in the sequence works because of the fifth axiom that defines the natural numbers, and that the next never skips over anything. If you start at 1 and you follow the next in the sequence, you will encounter every possible k value you can find, as long as you keep waiting, okay? As long as you just keep going through the process. And that is that induction step, that you're never going to skip over anything. And so you can verify it for all possible cases. All right, so let's start now with the first one. What we start with is okay, we start with, sorry, I was picking up my papers to find out where my notes are. So we start with k equals 1. So again, what we want to prove is, that we want to prove that the following holds. We want to prove that n plus the quantity m plus k, m plus 1 now, because we're saying, right, we're going to write down this star thing right here, but now I'm going to place k with 1, is equal to n plus m quantity plus 1. All right, so again, I'm going to circle that there. I'm going to square this off here. And I don't know if this is true, so we have to see if we can follow through with this. All right, so I'm going to start with my result. So I'm going to start here on this side. I'm going to take n plus m. And whatever that value is, whatever that sum, now what I'm going to do is, of course, I'm going to add 1 to it. Okay. All right, and this is the same thing as, this is equal to, of course, S n plus m. It's the next in the sequence. And that's by definition. I'm going to write this below it. That's by definition of the first identity. If I take the next of anything, so in this case n plus m is what I want to take the next of, I just add 1 to it. Okay, that's what we're doing there. Okay, and now what we want to do then is go, okay, so I'm going to do the same thing now. I'm going to say now I'm going to take n, and I want to add it to m plus 1. So that's equal to n plus s m. Okay, so, and that's again by definition. This is by definition of 1 as well, because I've replaced this object right here with that there. Now we got to examine this. All right, we already showed that if I have this here, this is equal to, and this is by number 2, that's equal to n plus s m. By definition of number 2 here. Again, these are given to us. We can use these freely without any problem. Okay, and so of course we note that these two are exactly the same, and so therefore we conclude that yes, n plus m plus 1, the quantity n plus 1 is equal to n plus m plus 1. So what we say is the associative does hold now for k equals 1. Check. All right, now we want to go back and prove it for other values of k. All right, so I'm going to go to the next page here. So again, I'm going to write up my definitions. Sn is equal to n plus 1, and also the following definition, S of n plus m, the next in the sequence is equal to n plus m, S of m. Okay, right, again, those are my two definitions. And now what I want to do is the induction step. So assume that n plus m plus k is equal to n plus m quantity plus k. Okay, what we want to prove now, we want to prove the same thing is true for the next in the sequence. We want to prove that that n plus m, the quantity m plus sk, is equal to n plus m plus sk. Okay, so we don't know if this is true yet, so I'll put that in the box and put a question mark on it. What we got to do is, of course, use our above two identities to see if we can get this to come out of it. Okay, so now again, we know this is true as well. We can take this for granted. We're actually assuming this is true, and to see what follows from it. So I'm going to take these three facts together and see what I can come up with. So the first thing I want to do now is I know these two are equal, and that means that the next in the sequence will also be equal to that. So what I can do then is go S of n plus the quantity m plus k, and that's equal to n plus m plus k, and I take the next in that sequence as well. All right, and they will be equal because the preceding identity was equal. All right, and let's say, remember, and then from 1, what can we get? And this is from 1 here. That means I can take this and now n plus m plus k, all quantity, plus 1. All right. So, and of course, now this is from 2. We can take this. Here was one of our elements. There was the other element. And now I can put that together. N plus m is equal to, plus sk, right? I can group those two together, all right, to create that. And of course, we see that equals this thing over there, okay? So we see that part is now, we can get it. Now we're going to go, and that was, of course, going from here, and we went this way, and these were all enchained together, and they were equal. Now I'm going to go on this side and see what I can do down there. So I'm going to take this and now see what I can make out of this. So again, I use the definition 1, and that's going to be n plus m, s of m plus k. All right, and that's by definition of number 1. Or sorry, that's number 2. I'm sorry about that. Okay. All right, and now of course I can and now I can use this result here. I can go forward and go n plus, and now I can look at this and deconstruct that further. That's equal to m plus sk. All right, and now what we see here is that is precisely this identity right here. Okay, so of course this is equal to that, and this is enchained together with equal signs all the way over to this. So this now has been proven. Check box and done. So now we have the associative property. The associative property is 2. Because it was true for k equals 1, and then any k after that is also true, which was this induction step that we just proved, it's true for all n, m, and k. Okay, so that looks good. Now let's go on. So again, what we've proven is the following: that that n plus m plus k is equal to n plus m quantity plus k. All right, and the idea here is that between the associative property is if you have two additions to perform, it doesn't matter which addition you start from once you write it out. Okay, so that looks good. So now what we're going to do is prove the commutative property. Okay, commutative property. We know the commutative property is this. For all n and m that are elements of the natural numbers, it's true that n plus m is equal to m plus n. And this is saying that order does not matter. Okay, order does not matter. All right, so let's see if we can establish this same property. And so okay, this property here. So now let's write down again what our hypotheses are. We're starting with n plus 1 is equal to the next. We have this second property that if I take the next of a sum, it's equal to the sum of the element plus the next of the next element. Okay, that looks good. But now we have the third property that we've just proven, the associative property that n plus m quantity plus k is equal to n plus the quantity m plus k. Okay. All right, so that looks good. Those are our 3 hypotheses we can use now to prove the associative property. So we're going to do this by induction again, but now what we're going to have to do is we have to start. We look at here. We have to look at all those combinations n and m, right? So what we really have to do is, to the start, is we have to fix m is equal to 1, and then assess. And then examine for all n. Okay, so let's do that. So let's start now. So we examine for all n. So we have to go through all these combinations. All right, and there's a lot of combinations. So we just have to start at the beginning. So of course, now we start at n equals 1. Of course, we know by definition 1 plus 1 is identically 1 plus 1. So that is m, that is n and m, and this is m and n. Okay, we know this, and this is trivially true. Okay, fine, check. All right, now let's assume, and this is the induction step. We're going to do an induction for all fixed m's. We're going to do this induction. Now that n plus 1 is equal to 1 plus n. We need to prove now. Prove that. Prove the following, that it's also true for the next in the sequence. Okay, so that looks pretty good. So we don't know this is true yet, right? This is still a question mark. So again, we have to take this statement and see if we can manipulate it using our 1, 2, and 3 to get it to look like this. Okay, so again, anytime you prove something, you really have to look back up at your hypotheses and use your hypotheses to get there. All right, so again, we can take this now. Because these are both equal by assumption, the next in the sequence will also be true. All right, and from here, we can, of course, do the following. We can write 1 plus s of n. Okay, so of course, that's already set there. Okay, good. All right, so now, of course, what we're going to do is, so we've already gotten to that point. Now let's go here. Let's go to the other side of this equal sign and see if we can utilize the same idea. That's 1. Oops, sorry. That's n plus s of 1. All right. So let's pull this out now. This is also going to, we can write this as follows. This is going to be n plus 1 plus 1, right? By definition. But we also know we have the associative property. So I'm going to call that A. That's going to be my new, that'll be, or sorry, I'm going to call that 3, right? That's this property right here, which is now that I can shift it. I can do this first. I can do that computation first, and then add 1 to it. And of course, that's equal to, by definition, and that of course is by property 1 here. Okay, and of course that is the following statement right there. And of course, because all of these are chained together in equal signs, it's true. So check that off. All right, so we've basically proven the following. We need to do this for all combinations, recall. So if this is n here, and that's m, we start at 1, 2, 3, 4, 5, and m is 1, 2, 3, 4, and so on and so forth up. When m is equal to 1, we've proven that for all of these combinations going this way. Okay. The question then is, what about all the stuff up here? We have to now verify that the order is true for all these other combinations up there. Let's see if we can get some insight into how to do that. Also, so what we really need to do then is look here. Look at this statement right here. We already see that that was our m right there. That was our s of m, right? All right. And so we can also write this as, at any rate, it's basically saying that if I take here, if I start here, I can also go up there. Okay? Right? So for n equals 1, I could go up there, or I could go up there as well. Okay? I can always go up. All right? I just need to find out now, if I'm up here at m equals 2, can I go over? And if I go over, if I can do this implication going this way, I can prove the orders don't matter going this way. I've done it for everything. All right, so let's see if we can lay out the groundwork for finishing this off. Okay, so now what we're going to do is, again, we're going to write down our properties, just like before. We had the following. N plus 1 is equal to Sn. 2, we have S of n plus m is equal to n plus s of m. And finally, the associative property that n plus m, the quantity n plus 1, m plus equals plus k, is equal to n plus the quantity m plus k. Okay, all right, those are our three properties. I always put them at the top just so we have a good bookkeeping here. And now we want to prove, now we want to assume that n plus m is equal to m plus n. We want to prove now that it's true that the next in the sequence will also be true. So we want to prove that Sn plus m is equal to m plus Sn. And also that we can always go up as well. Oops, sorry. Plus n. All right. It doesn't matter where you put the next in the sequence. You attach it to any one of your elements in any order, and it doesn't matter. They're all going to be equal to each other, and that is essentially proving for all those possible cases, right? Going out that way or going up, wherever you are, you can go both directions by adding another one to it. All cases are possible. Okay, so that's pretty straightforward. All right, so what we do, of course, is just like before, s plus m. We assume, of course, that this is true. So I want to know if this is true. I'm going to put that again in a box. I don't know if it's true. So I put that in a box and put a question mark on it. And I want to see if I can verify that these are equal. We're going to start with this assumption here. S plus m is equal to m plus n. All right, and now I'm going to take the next in the sequence, which will also be equal to each other because anytime the next in the sequence are equal, the previous are equal. All right, so and that's one of those axiomatic rules we have. All right, and again, this is defined as s plus m plus 1, and that's equal to m plus n plus 1. Okay, of course this is, oops, I keep writing s's where I want to write n's. There we go. All right. Okay, so that looks good. Now we just need to finish this off. Of course, that's n plus s of m. Where is that one? Right here. Okay, check. All right, and this one here is m plus n plus 1. And that's going to, of course, be m plus s of n, which is right here. Okay, and those are all equal. Okay. All right, and the next thing, of course, we could do is use the associative property. I'm going to take that down and set that equal, and that becomes m plus n. This is true now, and that's the associative property, or sorry, that's the commutative property for 1, okay, which we proved on the previous page, okay. And then, of course, now we have that as, we can use the associative property. Okay, that was the associative property, which is equal to s m plus n. Okay, there's this one right there. All right, and finally, we need to get this one. So if we go over here, and then I do the same process there. We know that 1 commutes. We'd proved that on the previous page. So those are equal. And that's equal to, I can then use the associative property. Okay, and that is equal to Sn plus m, which is this one right here. Okay, so they're all equal to each other. And then we've now proven that no matter which order we take, we can always make any one of the elements in any position the next element, and that will also be true there. Okay, so of course we've now proven, so we can check that off. We've proven the commutative property that n plus m is equal to m plus n. Okay, so in sum, we've taken our axioms, we've taken our essential hypotheses that define the algebra, and we've proved these essential shortcut routines that allows our algebra to be simple. Simple addition. Okay, so I hope you enjoyed this video and now have a clearer sense of how the counting numbers create algebra and what hypotheses are needed to make the algebra work in a sensible, simple way. All right, thank you very much.